Hello everyone. In this video we are going to introduce a robust two-layer MRAC framework to enforce competing constraints. Classical model reference adaptive control approaches cannot simultaneously enforce hard constraints on the tracking error and soft constraints on quantities such as actuator saturation. Existing adaptive control systems enforce hard constraints through the use of barrier Lyapunov functions. Barrier Lyapunov functions used to enforce a user-defined rate of convergence of the trajectory tracking error may lead to aggressive control effort. Furthermore, hard and soft constraints may compete with each other and eventually become incompatible. Hence, a way to handle this problem should be addressed. So, the objective of this work is to develop an MRAC framework able to simultaneously enforce hard constraints on the tracking error, enforce soft constraints on user-defined parameters, mediate between competing hard and soft constraints through an adaptive mechanism, be robust to unmatched uncertainties, enforce user-defined rate of convergence without leveraging barrier Lyapunov functions, decouple the tuning of the convergence rate from the reference model. This set of capabilities makes the proposed framework unique. Here we have an overview of the framework for two-layer adaptive funnel MRAC systems. This framework stems from an augmentation of the two-layer MRAC 1. Indeed, the plant, reference, and auxiliary reference model, as well as the control law, do not change with respect to the two-layer formulation. The major variations here are in the adaptive law, which comprises additional terms that allow to enforce constraints. Furthermore, the adaptive law makes use of the projection operator and dead zone operator to cope with the unmatched uncertainties. Here we have the additional terms present in the proposed controller's adaptive law. The constraint set and the constraint function h, together with the barrier Lyapunov function ve, are used to enforce hard constraints on the tracking error, while soft constraints are enforced using the function xi. In this case, the soft constraints take into account actuator saturation, having the hard constraints relax if the actuators are reaching saturation and having the hard constraints tighten if the control effort is low. We identify the constraint set as the funnel, since in nominal conditions the constraint set tends to shrink. In the h function we can identify the funnel diameter, which characterizes a time-varying barrier that cannot be crossed by the weighted norm of the tracking error. The funnel diameter is governed by the following adaptive law, where 5 different cases are employed. The first one is used to impose a safety margin between the funnel and the tracking error, to avoid overly aggressive control input. The second one represents the nominal case, where sigma-nom is the minimum between the value requested through the user-defined function xi and the maximum allowed contraction rate of the funnel, specified by lambdasat. The third case is used to impose an upper bound to the funnel diameter, while the fourth case is used to impose its lower bound. Finally, the fifth case is used to turn off the funnel adaptation. Here we have a diagram representing the functioning of the funnel adaptation mechanism. The gray area represents the nominal second case of the funnel adaptive law. The yellow area represents the first case, the light blue area the third case, the red area the fourth case, and the green area the fifth case. We'll now have a look at some numerical simulations used to assess the performance of the proposed algorithm. The top left panel shows the proposed control system. The central bottom panel shows the control system developed in reference 7 of the paper, while the top right panel shows the control system developed in reference 8 of the paper. In the mission, the UAV is required to follow the user-defined trajectory while carrying an unknown unsteady payload, which consists of 2 steel balls. The top plot shows the position tracking error, while the bottom plot shows the velocity tracking error. From those, we can see how the proposed control system outperforms both of the other 2 similar control algorithms developed in references 7 and 8 of the paper. We'll now have a look at some experimental flight tests used to assess the performance of the proposed algorithm. The proposed adaptive funnel two-layer MRAC system is compared to its classical two-layer MRAC counterpart. 2 types of mission are performed, one in nominal conditions, and one in off-nominal conditions involving an unknown sling payload attached to the UAV frame that has a mass equal to 27.6% of the vehicle mass. We performed 10 flight tests for each controller for the mission in the nominal case. Here, we are looking at 9 selected flights for the adaptive funnel two-layer MRAC framework. Here, instead, we are looking at 9 selected flights for the classical two-layer MRAC framework. We use the nominal condition mission to tune both controllers. For a fair comparison, all shared gains are kept identical. The only differences come from the additional gains introduced by the proposed funnel two-layer framework. Here is the plot of the norm of the trajectory tracking error versus time. We computed the mean and standard deviation for the 10 flights of each controller. From the plot, it emerges how, even in nominal conditions, the proposed controller outperforms its classical counterpart. Then, we performed 10 flight tests for each controller for the mission in the off-nominal case. Here, we are looking at 9 selected flights for the adaptive funnel two-layer MRAC framework. It is worth remarking how the tuning gains have not been retuned for the off-nominal case. In fact, they are equal to the ones in the nominal case. Here, instead, we are looking at 9 selected flights for the classical two-layer MRAC framework in the off-nominal case. Here is the plot of the norm of the trajectory tracking error versus time. We computed the mean and standard deviation for the 10 flights of each controller. From the plot, it emerges how, in off-nominal conditions, the proposed controller outperforms its classical counterpart. Additionally, here we observe the L2 norm of the trajectory tracking error versus time for both controllers in both mission scenarios. From the plot, it emerges how the performance of the proposed control system are affected much less by the unknown sling payload compared to its classical counterpart. In fact, remarkably, the performance obtained by the adaptive funnel two-layer MRAC framework in the off-nominal mission is better than that of classical two-layer in nominal conditions. The following table summarizes the results obtained in the experimental flight tests. All the metrics considered in the table show that the proposed framework yields improvements up to about 64% with respect to its classical counterpart, except for the maximum standard deviation of the norm of the trajectory tracking error in the nominal mission. However, this difference is marginal compared to the other performance metrics. Thank you for your attention. For more information, please contact Andrea Laflito or visit the website below. Finally, we would like to acknowledge the sponsor of this research.